So welcome students. In last weeks we have studied about the 5 different types of membrane based separation methods. First is the reverse osmosis, then the gas separation, then the perforation, then we will study about the liquid membranes, and at last we studied about the electrodialysis. Now in this week we will study about the membrane application in a different field. So in this week we will study about the membrane reactors. So basically membrane can also be used to facilitate the reactions. So in the so basically membrane reactor have the different type of application and different type of classifications. So basically membrane reactor is a device that combine the reaction and separation in a single step. So how the membrane works in the reactor, it can apply to provide the highly purified reactant to the system, or it can be used to separate out or to remove the purified product from the reactor, or it can be used as a catalyst or provide the surface area to the catalyst, because when you are using the heterogeneous reaction, then the surface area of the catalyst is a big phenomena, so it will be act as a contractor also, where the membrane will provide the surface area to react the to provide the surface to act as a catalyst. So here we have the different application of membrane can be employed as a introduce or separate or purify the reactant and products, to provide the surface for reactions, to provide the structure for reaction medium. So basically it is a new process, relatively new process, which is used to facilitate the reactions in the industrial scale reactors in different type of industries. So how the membrane reactors will work? So the functions of membrane reactor, how the membrane reactor will work: removal of the products. The membrane can be used to selectively remove one or the more product from the reaction zone to shift the equilibrium towards the product or support the unwanted and suppress the unwanted reaction. So basically, if you have the reversible reaction, suppose there is a reaction which is a reversible reaction, so to shift the reaction in the forward direction, you need to remove the product from the reactor, otherwise it will achieve the equilibrium. So for removal of the product from the reaction or from the reactor, you can use the membrane separation process. So here this is a reactor, this is the reactor reaction zone, this is the feed, this is the product P1, and this is the product P2. So here the reaction is like that, F equal to P1 plus F stands to P1 plus P2. So it is a reversible reaction. So it to suppress the backward reaction, you have to remove either P1 or P2 from the reactor from the reaction zone. So for that we use a membrane here. So Pa2 will be passed through this membrane. This is the sweep gas which will take the P2 from here. So P2 will pass through this selectively passes through this membrane. So this membrane is highly selective for P2, but this membrane is not permeable for the F and P1, not for the feed product and not for the P1 product. So once the P2 will remove from the system, the reaction will shift towards the forward direction. Okay, so it will shift the equilibrium towards the products. Okay, so this is the application of membranes in a reactant type of application. Now second application of the membrane reactor is through addition of the reactant in the control way. Suppose you have the several parallel reaction, and the selection of the reaction will depend upon the limiting feed or limiting reactant. So suppose you have an oxidation reaction which may produce either a different type which may produce CO2 or H2O or different type of intermediate products. So you want the specific intermediate product. For that you have to supply the oxygen in the control manner. If the oxygen is concentration is slightly higher, then the reaction will the parallel reaction will occur. It will convert it into CO2 and H2O, and it will be slightly lower, then the other reaction will occur. So you have to supply the reactant, in this case the oxygen, in the specific concentration. For that you can use the membrane reactor. So this is the F1 first feed, which is supplying from this is the reaction zone which is coming from here, and the F2 will supply from through this membrane. So it will come as a control manner. The concentration of F2 will remain constant throughout the reactor, industrial scale reactor, and you will get the precise product. So this is the another application of the membrane reactor in the industrial scale operations. Now membrane reactor can also be used as a catalyst. So suppose, because as I explained you that membrane separation is a surface phenomena, so we can arrange the membrane in the different manner which will increase the surface area of the membrane. So same concept can be used. So here suppose you have coated the membrane with the catalyst, or the pores of the membrane will filled with the catalyst. Now this is the F1, this is the F2. So reaction will occur inside the membrane, then the product will permeates through the membrane and comes to the other side, and you will get the different products. Okay, so this is the way you can use the membrane as a contractor. So it will membrane will act as a medium to which will allow to contact the two different feeds and produce the product, and product will be permeates out through membrane selectively, and it will comes from the different chambers. Okay, so in here the product P1 will come here and P2 will come here. How it will come? Suppose you have a reaction like HI is degraded in the H2 and I2. So the membrane pores will be highly permeable for H2, and it will be less permeable for I2, because of the size of molecule of iodine is much higher than the size of molecule of hydrogen, as well as the size of molecule of Hi is also very much larger than the size of molecule of the hydrogen. So hydrogen will be permeates out from the membrane. It comes to the other side and it can be removed, but Hi and I2 will not be permeates through the membrane. So this is the second type of application where the membrane itself act as a catalyst, or it will support the catalyst. Now the advantages of the membrane reactors. First is the compact design, because you are using the membrane reactor, otherwise you have to use the different chambers for different one chamber for separation, one chamber for reaction, then other chamber again for the separation. Here you have the compact design where the separation and the reaction will occur in a single chamber or inside a reactor only. No need the separation this step. And increase conversion, because in the equilibrium condition you are shifting the reaction towards the forward direction, so you can increase the conversion. Increase selectivity towards the product, it will increase the selectivity towards the product. Expand allowed range of the temperature and pressure, because you can you are using a single step for the separation, so you can also use it will expand the allowed range of temperature and pressure. How? Because the reactant and reactants can be entered in the reaction zone in the controlled manner, and product can be removed simultaneously. So the temperature and pressure requirement can be rearranged. Enhanced heat transfer in the series of the reactions. So you can also enhance the heat transfer by using the membrane processes. So because it is a controlled environment, you can enhance the heat transfer easily. Disadvantages of membrane based reactors is first is the membrane fouling. Membrane can be fouled. So if you want to run the reactor very long, periods. So you have to take care of this thing, that the membrane might be fouled with the time. And second thing, if the your reactant or the product will be very corrosive, then you have to select the membrane very carefully. Second is the high capital cost, because generally the membrane reactors are very costly. This is a emerging technology, and the expertise required to prepare the commercial scale membrane is much higher. So you need the very good expertise to prepare this type of membrane at the industrial scale operations, for the industrial scale operations. So the requirement of capital cost is generally high for the membrane reactors. Now the membrane reactor used for the specific purpose. So the membrane reactor used in the membranes used in the membrane reactor may be polymeric or inorganic. So different type of membrane can be used. It might be polymeric membrane, it might be inorganic membrane. The physical structure might be the porous membrane, symmetric, asymmetric. Different type of membranes can be used based on the requirement. So based on the specific application, you may change the membrane. A wide variety of membrane are used in this process. So it might be a flat sheet membrane, hollow fiber membrane, shell and tube configuration membrane. So the membrane reactor also be classified, especially in the biotechnology field or the biochemical processing field. It is also be classified as the submerged reactor membrane and the side reactor membrane. And in the catalyst field, it is classified as the catalytic membrane reactors and the packed bed membrane reactor. So there are two different type of reactors. One is in the bioreaction, it will be the submerged reactor or the side stream membrane reactors or the submerged membrane reactor. And in the catalytic reactor, it might be the catalytic membrane reactor or packed bed membrane reactor. So I will explain you what is the difference between the catalytic membrane reactor and packed bed membrane reactor. So basically in the catalytic membrane reactor, the membrane itself contains the catalyst. So membrane is either coated with the catalyst or the pores of the membrane is filled with the catalyst. And packed bed membrane reactor means the reaction site or reaction chamber is packed with the catalyst, and you have the membrane layer above it which will allow to pass out one of the product from it. So when you are talking about this application here, so suppose this chamber is filled with the catalyst, and here you have the membrane which allowed to pass out one of the product from here. So that type of membrane reactors is called the packed bed membrane reactor. And when you have this type of configuration where the membrane itself coated with the catalyst or membrane pores are filled with the catalyst, that type of membrane reactor is called the that type of membrane reactor is called the catalytic membrane reactor. Now the other classification of membrane reactor is the side stream membrane reactors and the submerged membrane reactor. So it will come under basically under the bioreactors. So first we will discuss about the bioreactor. Actually the membrane reactors are very good, have the very advantages in the biological field. How? Because in the biological field we generally need to separate out the products from the reaction. In the biological reaction, there are a lot of unwanted products are produced during the reaction, and that should be removed from the reactor, because that product also work to suppress the reaction. So there are three different types of biological reactor used, especially in the wastewater treatment: biomass separation reactor, aerated biofilm reactor, and extractive reactor. So it provides much higher separation ability and high loading rate in compared to the conventional system, excellent effluent quality and treatment possible under the extreme conditions. And the configuration, as I explained you, might be the side stream membrane reactor and the submerged membrane reactor. So I will explain you the different application one by one. So biomass separation reactor. Biomass separation of the biomass phase from the wastewater. This is reactor, that means basically if you have the biological waste in the water, or you want to remove the biological oxygen demand from the water, so So you can use the biological membrane based separation process. You can use the ultrafiltration membrane and the microfiltration membrane that can be easily remove the unwanted solid particles or the organic material, biological material present in the wastewater, that can be removed. Second is the aerated biofilm reactor. So if you want to go for the oxidation reaction, suppose in the wastewater treatment you want to oxidize the waste from the wastewater, or you want to convert the hydrocarbon or glucose to the alcohol, so you need a membrane which will provide the oxygen in the controlled manner. So controlled oxygen, addition of oxygen can be a, yeah, can be applied by using the, can be possible by using the membrane based process, membrane based reactor. So when you supply the oxygen in the controlled environment, then the space, you can grow a specific type of microorganisms in the feed stream, and which will leads to a specific type of product, because different the in the different concentration of oxygen, different type of microorganism will grow. So if you can control the amount of oxygen present in the feed, then you can control the reaction very easily. Then extractive reactor, in several times what's happened that the different unwanted product produced in the reactor and during the biological reaction, and that products will kill the microorganism. So you need to remove that product to shift the reaction towards the forward direction. So this type of unwanted products can be removed during the this process. So this is the extractive reactor. So there are three different types of biological reactor which are generally used to water purification as well as the other biological reactions also. One of the most important process which is used where the membrane reactor are used is the fermentation. In during the fermentation, what is the fermentation? Fermentation is to convert the glucose into the alcohol. So you are using the yeast. Yeast will oxidize the glucose in the alcohol. So during the fermentation, what's happened several times that when the alcohol will produce, that alcohol will itself act as an inhibitor for the reaction. So that alcohol, when the such at a certain concentration of alcohol will achieved in the reactor, then that alcohol will start to kill the yeast and the reaction will stop. So if you have a membrane reactor, then you can separate out the alcohol simultaneously with reaction, with reaction. So in this way you can shift the process. So alcohol will produce in the reaction and it will remove from the reaction. Then you can shift the process and you can work, you can use the fermenter as a continuous reactor. Generally fermenters are the batch reactor. If you study the biotechnology or the or the reaction engineering in the biotechnology, you will find that the most of the biological reactors used in the industries are the batch reactor. Why? Because after achieving a certain concentration of product, generally the microorganisms start to die. So if you have a membrane reactor, then you can easily separate out that you can easily separate out that products from the reactant, and you can achieve a continuous process. So now the two different type of membranes bioreactor, which are the submerged bioreactor and the side stream membrane bioreactor. So these are the two different type of configuration used in the biotechnology, especially biotechnology field. So if this is a bioreactor, it is a big jar or the batch bioreactor, and you want some type of products are produced inside the bioreactor and you want to remove that product. So either you can, and the whole bioreactor membrane based separation module will be submerged inside the bioreactor. Here the membrane based separation setup will be inside the bioreactor, and here the membrane based and the second design is when the membrane based bioreactor is bioseparator is outside the reactor. So this is the system which separate out the product, and it is outside the reactor. And here in this design, this is the system which is separate out the product, and it is inside the reactor. So how these two type of uh, separation process design are different. Basically, if the system is inside the reactor, then there is a more chance to foul the foul the membrane. Why? Because the bacteria will start to grow on the surface of the membrane also. And they may grow on the surface of the membrane, and they may block the membrane pores. So the fluxes are less inside this reactor. And the second thing is, you cannot apply very high driving force when the membrane is itself submerged inside the reactor. So you cannot apply very high driving force. So in the submerged reactor, fluxes are low. In the side reactor, you may achieve the higher fluxes, because you may achieve you may apply the higher driving force. Cleaning is not easy in the submerged bioreactor. It is less frequent, and in the side bioreactor you can easily clean the reactor. You can stop the this circulation, and you can clean the reactor very easily. Capital cost is high in the submerged reactor. The type of design of the membrane separation system required for the submerged reactor is costly than the type of design of the membrane separation system required in the side stream membrane bioreactor. And the operating cost is low here, because you not required a pump to flow the liquid, and the operating cost is slightly high in the side stream membrane bioreactor. One more important advantage of the membrane submerged based membrane reactor is that if you are using the membrane system outside the bioreactor, then when the fluid will flow from the outside bioreactor, the condition which you maintain inside the bioreactor will be changed. And because when you work in the specific type of reaction, bioreaction, then sometimes it is also very important to maintain the specific type of bacteria. So this fluid should not be contaminated. Okay, so suppose some foreign microorganism enter inside this chamber, then it will kill all the useful microorganisms present in the reaction. Okay, so basically if you flow the reactant outside the reactor, then it is somehow dangerous. It may kill your microorganism also. Here you need to use some type of pump to flow the feed from the outside the reactor, and then recycle it inside the bioreactor again. So you need pumps also, you need tubing also. So it may contaminate your the reactant present inside the reactor, as well as it may kill the microorganisms. So the submerged bioreactor are much more useful when you want to proceed a specific type of reaction. Now the other type of membrane reactor which is very useful is the perforation reactor. So perforation reactor, as I explained you, I give you the example of the separation of ethanol from the fermenter. So there we use the perforation, because water and the ethanol make the azeotropic solutions. So if you want to remove the separate out the ethanol from by using a membrane based process, then you have to use the perforation process. That's only you can separate out the ethanol from the water. So basically you have the glucose solution which is treated inside a fermenter, and you mix some yeast there. So it will the yeast will consume the glucose and produce the alcohol. Now the reaction will stop after some time, and if you don't want to stop the reaction, then you have to just separate out the ethanol, because ethanol is a poison for the microorganism. So it will kill the microorganism. So you want to separate out the ethanol from the fermenter, so you can use a membrane based separation process, and the only membrane based separation process which can separate out the azeotropic solution ethanol and water, that is the perforation. So perforation is very useful for such a reaction where you produce the azeotropic mixture, and you want to separate out the azeotropic mixtures. So basically here evaporation works on the principle that one side of the membrane is exposed to the liquid phase and other side is maintained at under vacuum, which provide the driving force for mass transfer across the membrane. So I have already explained you about the evaporation process in the detail. So how it's work. So situated dilute reacting system, slow reaction, non-volatile products or the imperfect membranes. So basically the product is very it means like the example of the ethanol. So the equilibrium concentration is only the 9% or the up to the 11%. So you cannot proceed the reaction when you have the 11% of ethanol. So if you want to produce the more ethanol, you have to separate out the ethanol simultaneously to the fermenter. Okay. And perforation based membrane reactor have the ability to separate the mixture near the azeotropic point, which I have already explained you. So it preferred over the reactive distillation and the other hybrid separation process. So this is a novel separation process. Otherwise you have the fermenter at one side, then you have the distillation column in the other side. First you ferment the feed, then you are sending the feed to the distillation, then in the distillation you have a lot of energy consumption. So in the distillery there are a lot of energy consumption due to this process. That's why it is called distilleries, because first you have to go for the fermentation reaction, then you have to distill the ethanol. You have to concentrate the ethanol because the initial concentration of ethanol is very less in the basic reactant. So you have to separate out the ethanol or concentrate the ethanol. So if you are using the perforation process, you can easily concentrate the ethanol with very less energy consumption and very less effect on the environment. It is also used for esterification reaction. So this is the diagram of the perforation process. This is the tubular membrane. Inside the tubular membrane you have the reactant which react and produce the ethanol. Ethanol will selectively diffused out from the membrane, and some of the water which will comes with the ethanol can be absorbed with the absorbent, and the pure ethanol can be collected here or outside the vacuum pump, and the reactant reaction will be occur inside this tube. It will be a continuous reaction. So you can shift the reaction equilibrium up to the higher conversion. The membrane used might be the hydrophobic or hydrophilic. If you are removing the water, then it might be the hydrophilic membrane. If you are removing the ethanol, it may be the hydrophobic membrane. Now the third application of membrane reaction is the partial oxidation reactions. So in the partial oxidation reaction, suppose you want to produce aldehyde from the ethene. So you can oxidize the ethene in the aldehyde, but there is a parallel reaction also. If oxygen is present in the higher concentration, then the reaction might be lead to this reaction where you end up with CO2 or H2O, and if the product is not removed simultaneously with the reaction, then also you might end up with CO2 or H2O. This is a series reaction also, this is a parallel reaction also. Okay, so this is an intermediate product which you want to separate out. So you can maintain this reaction, you can produce the aldehyde efficiently by supplying the optimum amount of oxygen towards the inside the reactor, as well as by removing the aldehyde simultaneously from the reactor. Okay, so both type of reaction application will be helpful here. First is you can supply the oxygen in the optimum amount by using the membrane reactor, so that reaction will proceed this first path only. Reaction will not proceed in the second path, and you can simultaneously remove the aldehyde from the reactor, so that the reaction will not proceed again further for the third path. It will stop up to here only. Okay, so this is the application of the membrane reactor in the partial oxidation reactions. And the last is the application in the hydrogen production. So there are a lot of different ways to produce the hydrogen in chemical processes and the thermal process. There are different ways to produce the hydrogen, and generally the hydrogen production reaction is either the reversible reaction or the series of the reaction. Suppose you are taking this example, if you have this reaction may further proceed to produce H2O also, and because hydrogen is unstable, if the slight amount of oxygen is produced in between the reaction, it will lead to the water production. So you have to remove the hydrogen simultaneously to from the reactor. And second advantage is the size of hydrogen molecule is generally very less than the size of other molecules present in the reactant. So the size of methane, water, CO, or CO2 will be much larger than the size of the molecule of hydrogen. So you can easily separate the hydrogen from the reaction, but the reaction is highly exothermic reaction. These are the reaction which occurs at the high temperature and pressure. So you need to use some type of metal reactor or the ceramic reactor. You cannot use the polymeric reactor membrane in this case. You have to use the metal membranes or the ceramic membrane in this case. So greater conversion in comparison to the conventional reactors, since overall reaction is the endothermic reaction. Pure hydrogen recovered using the palladium reaction. So basically you can also control the reaction in this condition. You can also control the reaction so that the temperature drop will be minimized throughout the reaction. Okay, pure hydrogen recovered using the palladium membrane. Temperature and pressure range is more convenient. Sweep gas can be used to permeate site for increasing the driving force. So how to make a driving force for removal, for removing the hydrogen from the other side, or from transferring the hydrogen from the feed side to the permeate side across the membrane, you have to produce some type of driving force. So that can be produced by sweep gas, or that can be produced by applying the vacuum. Okay, so this is the different examples of the application of membrane in the reactor. So this is a very emerging field, and several now the membranes are used in the several different type of industrial scale reactors. So the basic advantage is you are shifting the reactions, so the conversion is high. You can select the specific type of reaction in the group of the parallel and series reaction. So you need a specific type of product, intermediate product or end product, from the different type of intermediate and end products. So you can use the membrane reactor. You can reduce the energy consumption, because you can reduce the capital cost. Why? Because when you use the membrane reactor, the you need only a single chamber for reaction as well as separation. So you need not to transport the fluid from the reactor to the separator. Then you have to again give the energy for separation, then you have to remove the energy from the separator. So that process, that steps can be removed during this membrane based separation process, or excluded from this membrane based separation process. So the capital cost will be low, as well as the operating cost will be low in the membrane based reactors. And the other advantage is you can improve the conversion. You can choose a specific product. So this is all about the membrane reactors. Now one or two more applications of membrane is remaining, so I will cover that in the next week.